In the previous session, we tried to understand the impact of the tilt of the Earth's axis on the apparent movement of the Sun, in the sense that how the altitude of the Sun is being varied because of the Earth's revolution, given the fact that its axis is tilted. Now, in terms of this Earth-Sun relationship, we shall move ahead and try to know how these two put together, that is, the tilt of the Earth's axis and also the apparent movement of the Sun and the variation in the solar altitude, how the intensity of the incoming solar radiation is being varied. Look at this particular question. There are two statements given again. The first statement says that the locations at the equator show the least amount of variation in insolation over a 1 year period of Earth's revolution, and the second statement says that the most extreme variations in solar insolation received in the southern hemisphere occur at 90 degrees south. These two statements again clearly conceptual in nature, and if you want to answer this question and if you have learned these concepts earlier, please pause the video and answer this question. Try to put your answers in the comment section. Those who have got the right answer, we are really good. In the previous sessions, we learned that the Earth's seasons are controlled by changes in the duration and intensity of solar radiation in terms of insolation, and both of these factors, as we have learned, are in turn governing the annual change in the position of the Earth's axis relative to the Sun. As I told you, even though the Earth's axis is constantly pointed towards the northern star in terms of its rotation, in terms of revolution, it is changing its position relative to the Sun, and because of this, yearly changes in the position of the Earth's axis occurs, and these changes in the Earth's axis cause the location of the Sun to wander at 47 degrees across our skies, as we have learnt in the previous session. So changes in the location of the Sun in terms of its apparent movement have their direct effect on the intensity of solar radiation. So the intensity of solar radiation is largely a function of the angle of incidence, that is, the angle at which the Sun's rays strike at the Earth's surface. Angle of incidence. I repeat, the angle of incidence is the angle at which the Sun's rays strike at the Earth's surface. So if the Sun is positioned directly overhead or 90 degrees from the horizon, then the incoming solar insolation strikes the surface of the Earth at right angles and is hence most intense that you can find. However, if the Sun is 45 degrees above the horizon, the incoming solar radiation occurs in a slanted position and it hits the Earth's surface at an angle of 45 degrees, and hence this causes solar insolation to be less intense. The primary reason why this less intensity of solar radiation when it hits the Earth's surface at an angle is because of the fact that this causes the entire rays to spread over a larger area. As you see in this particular picture, if it is straight, it is clearly hitting the region at 90 degrees and hence it is more intense. However, when it is trying to hit at slanted position, it is covering the larger surface area, and because of this, it gets spread over this larger surface area, and hence it in turn causes a reduction in the intensity of the radiation. So the surface area is approximately 40% greater than whatever the area that is covered by this angle of 90 degrees as an angle of incidence of the solar insolation. So the lower angle also reduces the intensity of the incoming rays by at least 30%, as per the graph that is clearly showing you. If you look at this particular graph, you find that if the solar radiation is occurring at 90 degrees, where the Sun altitude is exactly at 90 degrees, the intensity is very, very high. That means if the altitude is 90 degrees, you find that the incoming solar insolation is occurring at 100%. If I am taking into consideration only the incoming radiation without looking at the various phenomena which also occur simultaneously, such as reflection, and if I take into consideration only the incoming solar radiation without looking at reflection and absorption as the concepts which are also associated with incoming solar insolation, I find that there is 100% incoming solar radiation when the Sun's altitude is at 90 degrees. However, on a particular day, when you find that the solar radiation is occurring at 0 degrees, that means when it is at the western horizon or the eastern horizon, you find that the incoming solar radiation is 0. Hence, the angle of incidence clearly defines the incoming solar insolation. This is the first point that you must remember. Secondly, here you must also remember that this clearly tells you the sine curve, and hence the incoming solar insolation and its angle of incidence, if I associate it with the sine formula, then you find that it gives you the insolation intensity. That means if A is the altitude, and if I use this expression sine A, it gives me the incoming solar intensity. That means if incidence is 90 degrees, then sine 90 is 1. That means it is 100%, which is arriving at the surface of the earth. And if it is occurring at 45 degrees, then you know that it is half. That means only 50% of solar insolation is reaching in terms of its intensity in comparison with the angle of incidence, which is at 90%. And if it is 0, then it is also sine 0 is 0, and hence there is 0 intensity which can be seen in comparison with when the sun is just overhead. So sine altitude will give you the intensity of the incoming solar radiation, given the fact that A is the angle of incidence. So if you look at this particular graph again, you find that the locations at the equator show the least amount of variation in insolation over 1 year period. I repeat, the locations at equator show the least amount of variation in insolation over a 1 year period. This is because of the fact that there is slight change in the insolation that occurs from these annual changes in the altitude of the sun above the horizon, as the duration of the daylight at equators is always 12 hours or above that. And hence, if you look at the peaks in insolation intensity, they correspond to the 2 equinoxes when the sun is directly overhead. The 2 annual minimums of insolation occur on the day of solstices. And hence on these days the maximum height of the sun above the horizon reaches an angle of 66.5 degrees. As I told you, it varies from 23.5 plus to 23.5 minus. That means it varies to the tune of 47 degrees in terms of its altitude, and the least altitude that is possible at equator is 66.5, because when at 90 degrees it is overhead, the least level of variation that is possible in terms of altitude is 66.5 degrees, because 90 minus L must give you the answer, and hence 90 minus 23.5 must give you the 66.5 degrees as the answer. So the least altitude that is possible here is 66.5, and hence whatever the annual minimums that you are seeing that is occurring on the day of solstices, and the maximums are occurring on the days of equinoxes, and if you compare these two, the amount of insolation in terms of its variation is least, because sine 90 is giving you 100% incoming solar insolation, and sine 66.5 will give you approximately a value near to 90%. That means in terms of solar radiation there is variation only to the tune of 10%. However, if you look at the most extreme variations that occur in terms of insolation, it occurs at the poles. And in northern hemisphere it has to be the 90 degrees north, and in the southern hemisphere it has to be 90 degrees south. Because if you observe the June solstice, you find that the 90 degrees north receives more potential incoming solar radiation than any other location that is being graphed in the above graph. So at this time the sun never sets. In fact, it remains at an altitude of 23.5 degrees above the horizon, as we have understood, for that whole day. And on some September from September equinox to the March 21 or March equinox, no insolation is received in this particular latitude, that is 90 degrees north, that is North Pole. So during this period, the sun slips below the horizon, and as the northern regions at this particular latitude of 90 degrees, they are always tilted away from the sun. There is complete darkness that you see. That means 0 degrees as the possible solar altitude. If you take into consideration, sine 0 will give you 0 degrees, and sine 23.5, which is the maximum value that is possible because of the solar altitude, you find that it is near 40%. That means the variation is maximum in this particular region between 0% to 40% in terms of the solar insolation and its intensity received towards the surface of the earth. So if you look at the question now particularly, you find that the first statement, which says that the locations at the equator show the least amount of variation in terms of insolation over a 1 year period, is correct because the variation is only to the extent of 10%. And the second statement, where it says that the most extreme variations in solar insolation received in the southern hemisphere occur at 90 degrees south, where in this particular statement he is specifically considering this South Pole. And in this particular statement, if I replace this with any pole as such, they receive the intensity where the variation intensity is maximum, because it varies from 0 degrees altitude to 23.5 degrees altitude, and the sine values of these particular altitudes gives you a variation of 0% to 40%, and hence the variation is really maximum when you look at the poles. So the annual variation in terms of insolation for these locations are obtained, and hence these two statements are correct. Hence the answer must be C. So this is one of the concepts that is important for the examination, which can be asked in the examination in terms of the Earth-Sun relationship that you can understand. In the next session, we shall look at the parallels and meridians as concepts, which are very important to find not only the location but also to understand the time zones in a particular location.